Hello, my name is Sergey Nosov. Today we are going to explore a critical security principle that I believe will fundamentally change how you think about building software systems. The principle we are discussing is called the boundary defense principle, and its core message is simple but powerful. Zero trust in every handshake. Before we dive in, I want you to keep this question in mind throughout the presentation. Where in your own code are you making assumptions about data coming from other components? Let me start with a question that might make some of you uncomfortable. When was the last time you trusted data from another service in your system without validating it? Most of us will admit we have done this. We have all written code that assumes the data we are receiving is safe, well-formed, or already validated. And honestly, that is completely understandable. It is how most systems are designed. But here is what I want you to think about. That assumption, that trust, is exactly where vulnerabilities hide. Most of us have internalized the idea that we need to validate user input at the edge of our systems. We sanitize form data, we check API payloads, we escape SQL queries when dealing with external requests. But the uncomfortable truth is this. The most devastating security breaches and data corruption incidents in modern systems do not happen at the perimeter. They happen at the invisible boundaries inside our architectures. Let me give you two examples. The 2017 Equifax breach exposed 147 million records. This was not because an attacker bypassed the front door. It happened because a vulnerability deep within their systems went unpatched, and the breach propagated laterally across internal boundaries that were assumed to be trusted. The Capital One breach in 2019 affected 100 million customers. Yes, it exploited a misconfigured web application firewall, but the real failure was that internal services trusted each other implicitly once past that initial checkpoint. In both cases, the systems had perimeter defenses. What they lacked was defense at every internal boundary. Today, I want to challenge a deeply embedded assumption in how we build software. The assumption that trust is transitive. That if component A trusts component B and component B provides data, then component A can safely consume it. This assumption is embedded in countless microservices architectures, serverless functions, and modular monoliths. And it is the root cause of catastrophic failures. The principle we are exploring today offers a different mental model. Trust is not transitive. Treat every interface as a trust boundary. Validate everything, everywhere, always. So let us start by expanding our definition of what constitutes a boundary. When you hear boundary, you probably think of the obvious places shown in the external category. HTTP endpoints receiving data from browsers or mobile apps, file uploads from users, third-party API integrations. But boundaries exist at every interface between components. Between services, your payment service calls your user service over gRPC or REST. That is a boundary. Your user service could be compromised, or a message queue could inject malicious payloads. Between layers, your controller passes data to your service layer. Your service layer reads from the database. Each of these is a boundary. Yes, even within your monolith. Between processes, your application reads environment variables, configuration files, or data from Redis. These are boundaries. Configuration can be poisoned. Databases can contain corrupted or maliciously altered data. The key insight here is that boundaries are not just at the perimeter of your system. They are everywhere. Let me visualize this for you. Here is a simplified microservice architecture. You have an API gateway at the top, several services in the middle tier, and shared infrastructure at the bottom. Every single connection you see here, every arrow, every line, is a potential attack vector or corruption point. If any one of these assumes trust without validation, your system has a vulnerability. This is why we need to think differently about how we architect systems. We cannot rely on perimeter security alone. We need validation at every one of these boundaries. Let me share a real production failure that illustrates this perfectly. This happened at an e-commerce company with a microservice architecture. The setup. They had a product catalog service that validated product IDs at its REST API boundary. It checked format, checked existence in the database. That sounds good, right? The assumption. The order service, which received product IDs from the catalog service via an internal event stream, assumed those IDs were already validated. After all, they came from a trusted internal service. The failure. A database migration bug in the catalog service began emitting malformed product IDs. The order service crashed immediately upon receiving these invalid IDs. Thousands of orders failed before anyone noticed what was happening. The mistake was not a lack of validation somewhere in the system. They had validation at the API boundary. The mistake was trusting that validation elsewhere was sufficient. The order service should have revalidated the product IDs it received, regardless of the source. The boundary defense principle is an application of zero trust architecture to your code base. In network security, zero trust means never trust, always verify. No user, device, or network segment is trusted by default, even inside the corporate firewall. Applied to software architecture, zero trust means exactly what you see on this slide. No component trusts data from another component, even if that component is internal, even if you wrote it yourself, even if it was validated upstream. This might sound paranoid. It might sound like overkill, but I'm going to show you why it is absolutely necessary. Why do we need zero trust? 3 fundamental reasons. First, components can be compromised. An attacker who breaches one microservice should not automatically gain access to all services. If your authentication service is compromised and starts issuing forged tokens, your authorization checks at every other service become your last line of defense. If those services trusted the authentication service blindly, the breach spreads instantly. Second, data can be corrupted. Networks fail. Message queues can deliver duplicates of or out-of-order messages. Databases can experience silent corruption. Caches can become stale. A service that reads from a database and assumes the data matches its schema is one schema migration away from a production incident. We saw this in the e-commerce example. Third, bugs exist. Even in your code, even in trusted services. A validation rule in an upstream service might have a subtle flaw. Perhaps it checks for SQL injection but misses NoSQL injection, or validates email format but does not check for homograph attacks. If downstream services revalidate, they catch what upstream services missed. These three reasons, compromise, corruption, and bugs, are not hypothetical. They're real, they happen constantly, and they are why we need defense at every boundary. Now, let me introduce the concept of progressive hardening. Traditional defense in depth imagines concentric walls, a firewall, then a WAF, then application level checks. An attacker must breach all layers sequentially. Progressive hardening is different. Each layer does not just add another wall. It revalidates assumptions and narrows trust. Let me walk you through a payment process and flow as an example. Layer 1, API gateway, validates HTTP structure, checks the authentication token, confirms the user is authorized to make payments. Layer 2, service layer, revalidates the payment amount. Is it positive? Does it match the currency precision rules? Rechecks authorization against business rules. Does the user have sufficient balance? Sanitizes merchant identifiers. Layer 3, database layer, enforces constraints, foreign keys, not null conditions, check constraints to catch any corruption or logic error that slipped through. Layer 4, audit layer, before committing the transaction, performs a final integrity check. Do debits equal credits? Does this transaction make sense given recent history? Notice something important. The payment amount is checked 4 times in different ways by different components. This is not redundancy for its own sake. This is resilience. If a bug in the API gateway lets through a negative payment amount, the service layer catches it. If an attacker exploits an SQL injection vulnerability to bypass server's layer checks, database constraints catch it. If both fail, the audit layer refuses to commit the transaction. One component failing does not cascade into catastrophe. Let me make this concrete. What does boundary defense look like in actual code? There are 3 pillars: validation, sanitization, and normalization. The first pillar is validation. Validation answers the question, is this data what I expect? You can see an example on the slide. At every boundary, you check multiple things. Type validation. Is this an object? Does it have the required fields? Range validation. Are values within acceptable bounds? In this case, is the order amount positive and below a reasonable maximum? Format validation. Does it match expected patterns? For example, does the order ID follow the correct format? Business invariance. Are relationships consistent? Does the order contain at least one item? The critical point here is that you perform these checks even if the data comes from your database, from another internal service, or from a configuration file. Never assume, always validate. The second pillar is sanitization. Sanitization answers the question, could this data be weaponized? The slide shows three common scenarios. For database queries, always use parameterized queries. Never use string concatenation. The database driver handles the escaping for you, preventing SQL injection. For rendering user content in HTML, use context-appropriate encoding. The HTML escape function prevents cross-site scripting attacks. For executing shell commands with user input, use shell escaping functions like shellx.quote to prevent command injection. The key insight here is that sanitization is context-specific. Data that is safe in one context, say JSON, can be dangerous in another context, like HTML, SQL, or shell commands. You need to know your context and escape appropriately. The third pillar is normalization. Normalization answers the question, are we talking about the same thing? Look at the three email addresses at the bottom of the slide. To a human, these all refer to the same user. But to naive string comparison, they are different. One has standard case, one has mixed case, one uses plus addressing. An attacker can exploit these inconsistent representations to bypass validation. For example, if you block admin@example.com, but do not normalize case, an attacker can use capital A admin at capital E example.com to sneak through. The code example shows normalization in action. Trim whitespace, normalize case, strip plus addressing. Now all three variants map to the same canonical form and your validation logic works correctly. Normalization ensures you are comparing apples to apples. It prevents bypasses via alternate encodings. Now, I know what some of you are thinking at this point. This sounds expensive. Validating at every boundary will kill performance and slow development. You are absolutely right to be concerned. Let me talk about the trade-offs honestly, starting with performance. Yes, validation has a cost. Parsing JSON, checking regex patterns, sanitizing strings, these operations consume CPU and add latency. But there are pragmatic approaches. Validate exhaustively at the system edge, your user-facing APIs. Then rely on strong typing for trusted internal paths. If your services communicate via strongly typed gRPC with schema validation built in, you can be more permissive internally. Cache validation results when you are processing the same data repeatedly. Do not revalidate the same email address 10 times in a single request. Profile your hot paths. Optimize the critical 5% of validation code that accounts for 95% of the overhead. Accept the overhead for security critical operations. For authentication, payments, privilege changes, the cost is absolutely justified. For read-only, non-sensitive queries, you might relax a bit. Rule of thumb: the closer to untrusted sources and the more security sensitive the operation, the more validation overhead is justified. The second trade-off is development velocity. Strict validation everywhere can slow internal prototyping. You want to iterate fast, not write validators for every field. Again, there are pragmatic approaches. Use schema validation libraries like Zod or Joy that generate validators from type definitions. You write the schema once, and the validation code is generated automatically. Build reusable validation utilities for common patterns: email validation, phone number validation, currency validation. Do not reinvent the wheel every time. Track validation depth like technical depth. Mark areas where validation is deferred for prototyping, but those areas must be hardened before production. Enforce validation in your CI/CD pipelines. Fail builds if public APIs lack validation tests. Make validation a gate, not an afterthought. The upfront cost pays dividends. Validation first design catches bugs early, before they reach production, before they become emergency security patches at 2 a.m. The boundary defense principle is not just a set of techniques. It is a mental shift in how we think about system architecture. The old mental model says, I validated this data at the API gateway, so internal services can trust it. This is transitive trust. This is where vulnerabilities hide. The new mental model says, every component is an island. Every component validates its own assumptions. Trust is never inherited. It must be re-earned at every interface. This shift makes systems more resilient, not just to attackers, but to bugs, to configuration errors, to schema drift, to all the ways that complex systems fail in production. It makes you think differently about APIs. Instead of designing for the happy path, assuming colors send well-formed data, you design for adversarial inputs and buggy clients. Your code becomes defensive, robust, and self-documenting. I want to leave you with one final thought. The next time you write code that crosses a boundary, calling another service, reading from a database, processing a message from a queue, pause and ask yourself, am I trusting this data? Should I? That pause, that question, might prevent the next incident. It might catch the bug before it reaches production. It might stop the breach from spreading beyond one compromised service. Yes, the boundary defense principle requires discipline. It requires an upfront investment in validation infrastructure. But the alternative, trusting data across boundaries without verification, is how breaches happen. It is how data corruption spreads. It is how one small bug in one microservice brings down an entire platform. I want to open this up for discussion. Here are the 3 questions to get us started. Where in your current systems are you trusting data across boundaries without validation? Think about the internal APIs, the service-to-service calls, the database reads. Where are the gaps? Second question. What would progressive hardening look like in your critical paths? Think about authentication flows, payment processing, data ingestion pipelines. How many layers of validation do you have? How many should you have? And finally, how can you balance validation overhead with performance requirements in your high throughput services? What can you cache? What can you optimize? Where is the overhead justified? Thank you all for your attention. I hope this principle resonates with you and changes how you think about building secure, resilient systems. Remember, validate everything, everywhere, always.